Every time a machine learning model makes a judgment, it carries the risk of being wrong. But not all errors are created equal. A system can fail in two entirely distinct ways, and the real-world toll of those failures almost never carries the same weight. To track exactly how our models are failing, we use this 2x2 grid, known as the confusion matrix. It serves a single purpose. It separates actual reality, along the columns, from the model's predictions, along the rows. When our model works perfectly, its predictions map directly onto reality. This creates a diagonal path of success, illuminated here in bright green. We call these the true positives, where the model accurately identified a target, and true negatives, where it correctly ignored something irrelevant. Generating this foundational layout for any classification model takes exactly one single line of code in Python. You feed it the true data, you pass it your model's predictions, and it returns the grid. Checking that green diagonal only tells you that your model is somewhat functional. To actually debug a system, engineers must investigate the dark space of the remaining empty squares. Those empty squares flashing red on the anti-diagonal are where algorithms cause real damage. We classify these failure states into two camps: false positives, also known as type 1 errors, and false negatives, known as type 2 errors. To master this, you need to lock down the naming convention. The terms positive or negative strictly refer to what the model guessed. The terms true or false refer to whether that guess actually aligned with reality. If your model claims an image contains a stop sign, it made a positive prediction. If there is actually no stop sign on the road, that prediction is false. Nailing this vocabulary is the mandatory first step to diagnosing how your system will impact actual users in deployment. Let's look at this balance scale to see why the distinction matters. In medical screening, a false positive means we tell a healthy patient they might be sick. It causes temporary anxiety and requires another blood test. But a false negative sends a critically ill patient home without treatment. The cost of a false negative heavily outweighs a false positive. Now, consider a spam filter. The scale flips entirely. A false negative means a single piece of junk mail slips into your inbox, a minor annoyance. But a false positive routes your boss's urgent project email directly into the trash, which can halt a critical project or end a career. The mathematical cost of an error is just a number until you account for the specific human stakes of the application you are building. Cautionary. This brings us to the accuracy trap. When evaluating models that search for rare events, default accuracy metrics will actively lie to you. This pie chart shows a medical model hunting for a disease that affects exactly 1 in a million people. We achieve a 99.9999% accuracy by hard-coding a single rule: output negative for every single patient. Beneath that high score, the failure is total. Because the model defaults to negative, it misses every sick person, resulting in a 100% false negative rate. The model satisfies the accuracy metric while failing its primary objective. Let's lock this in with a quick exercise. Pause the video. Look at these two brief arrays, the true labels on the left and the model's predictions on the right. Manually sort these 5 predictions into the empty 2x2 grid. Let's map them together. The first pair is a 1 and a 1. That's a true positive. Then a 0 and a 0, a true negative. Next, reality is 1, but we predicted 0, giving us a false negative. A 1 and 1 gives us another true positive. Finally, reality is 0, but we predicted 1, dropping into the false positive quadrant. Relying strictly on a top-level accuracy score blinds engineers to catastrophic, specific failure modes. The confusion matrix forces you to look at the exact distribution of your mistakes, making it an absolute requirement for responsible development. To optimize against these specific errors mathematically, we use the syntax shown in the code snippet here. By calling the ravel function on our confusion matrix, we extract the exact raw counts for each quadrant into 4 distinct variables. Pay close attention to this next detail. The popular scikit-learn library flattens this matrix in a highly specific, non-intuitive order: true negative, false positive, false negative, true positive. You must memorize this exact sequence, or you will accidentally optimize for the wrong error and ruin your model. As you can see in this cheat sheet, treating all errors as equally bad is the mark of an amateur. You have to know which error you can least afford, the doctor's nightmare or the spam filter's nightmare, before you write a single line of architecture. Now that we have successfully isolated and categorized our errors, our next challenge is translating these raw quadrant counts into actionable mathematical ratios. We need to measure exactly how many flagged items were actually right versus how many right items were actually flagged. That brings us to precision and recall. Intelligent system design requires balancing correct answers against the mathematical necessity of choosing the safest way to be wrong.